Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series on applied electronics. We are starting afresh the subject intended for semester 4 on basic physics on the chapter on optics. The whole content of this chapter starts from defects of images, a very important area, spherical aberration in mirrors and lenses, method of minimizing spherical aberration, chromatic aberration, achromatic combination of lenses in contact, etc. It ends with uses of polarized light. This is a syllabus intended under optics chapter, and this is a unit 1. And as I told you, we start with defects of images. Again, I will emphasize is a very important area because of the fact that the images that we obtain about star or moon or any other planet, and not only the images that we capture of microbes using a microscope. Now, all these images that you obtain may be far from the actual shape and size of the original image. So, if there is a deviation between the original image and the image you capture using a microscope or a telescope, as I told you, you get the the dynamics of a star or the image of a star or a planet like Venus or Mars. All these things are obtained using a telescope. Now, I will tell you, I am seeing you, the persons who are sitting in front of me, and I see them through a lens. I have got a lens in my hand, and the image that I observe without the lens and with the lens will be different. Eye is a, the eye has got a lens. The best lens one can think of, before we made the lenses, God has given or nature has given the lenses to us. Eye has lenses, and the eye lens is the one that makes us to see objects. And if the eye has defect, then the defect will be rectified. Otherwise, this image that we will be observing will be defective. I think this is the best or the simplest way in which the defects of images can be explained. What I would like to tell you now again, you see an image, you see an object with your eye, with the naked eye, and then with the lens or the one you are wearing the lens, right. Now, aged people have to wear lenses, otherwise they will not be able to read the numbers. So, the numbers will not be seen properly. So, that is the image, the numbers will be seen will be appearing to be blurred, right. The images, when you go to optician, he will ask you to read the letters and the numbers. Why are you asked to read the letters and numbers? The numbers and letters, they appear to be somewhat defective and they are to be corrected, and that is the reason why you are wearing a corrective lens. So, the images that you see appear to be defective, and the defect is due to your defective eye lens. So, eye has got lenses, as I told you. Eye lenses ought to be corrected, and you have to use proper spectacles to see the proper images. Otherwise, you will be seeing blurred images, or the nature of images that you are obtaining using the lenses and mirrors will be different. Now, instead of the eye lens, I will be talking to you about the objects. You are using a telescope, instruments like a telescope or a binocular or a microscope, or you are all interested in photography. So, the photographs you take with your camera, the image that you capture may be defective because of very many reasons, and how to correct the images. That is the objective of this lecture 1, and the whole chapter, that is unit 1, will consist of spherical aberration that you have in mirrors. The spherical aberration again due to lenses, coma, astigmatism, curvature of the field, distortion, chromatic aberration, and chromatic aberration caused by a lens, and how they can be, the defect can be rectified using a achromatic lens. Now, let us start again with the contents of this lecture, namely what are aberrations. First of all, when we are talking about defects of images, what do you mean by defects of images, or what do you mean by aberrations? What are the causes which lead to aberrations? Aberrations of images, what kind of images are obtaining, what are the defective images? I will show you what kind of defective images that you are obtaining, and what are the factors which are responsible for the defective images that you observe through the telescope or through the microscope or through the binocular or through your camera. What you really see and what you capture may be different. Right? I will show in a moment what kind of images you will be obtaining. And lastly, in today's lecture, we will be seeing spherical aberration in mirrors and lenses. So, let us begin with the question, what are aberrations? The grammatical meaning of aberration is deviation from the reality. The real object is the one that one has to see, but the one that you see is different from the real image. It is a defective image. The departures of real images from the ideal images in respect of the shape, size, shape and position are called aberrations. So, the deviation in the image that you perceive, that you observe, when you observe a star using a telescope, or you observe a microbe through a microscope, or whatever you are capturing through a your camera, the image may not be the real image. It may have a defect, it may have some one or more defects, and again the eye has got defect. So, the younger people are using lenses, they are using spectacles, and the older people also are using spectacles. The reasons are for two different reasons. Anyway, otherwise the image that you see or the image that you perceive will be a defective image. So, an aberration is any failure of a mirror or a lens to behave precisely according to the simple formulae connecting u, v and f. All of you know how you define the focal length in the case of a concave mirror. If you say f is the focal length of a concave mirror, you write 1 by f is equal to 1 by u plus 1 by v, where u and v are the object distance and the image distance. These things you would have studied in high school, and anyway these formulae are incorrect under certain circumstances. I will tell you later under what circumstances these formulae become approximate or incorrect. They are inevitable consequences of the laws of reflection and refraction at spherical surfaces. Now, let me show you what is the problem that you are encountering in a case of mirrors. If you got a mirror of this shape, it is a concave mirror, as all of you could see, the concave mirror, the light rays are incident on the concave mirror. So, what about this ray 1? If you call this ray 1, this ray will undergo a reflection and will meet on the optic axis at this point, and similarly this ray will come to a focus at this point, right. Whereas, these light rays that are nearer to the optic axis, right, this light ray is called a paraxial ray. These light rays, these two light rays are paraxial rays because they are very close or parallel to the optic axis. All of you know this is the optic axis, right. So, light rays which are closer to the optical axis, they are called, or parallel to the optic axis, they are called paraxial rays, and these light rays will come to a focus at this point. Whereas, these light rays which are hitting at the mirror at the edge, at the peripheral edge, they are called the marginal rays. So, these light rays that are called marginal rays, these two rays. So, the marginal rays come to a focus at this point, whereas the paraxial rays come to a focus at this point, and so you will be having many focal points. So, you have got an object here, the light coming from the object will not be getting focused at a particular point. So, you have many foci, many focal points are there. So, you have got a focus here, another focal point here, another focal point here, another focal point here. Instead of a point object, you will be having number of foci, number of points at which you will be getting the image getting converged, the light rays being converged. This leads to what is called spherical aberration. This is called a spherical aberration. A spherically shaped mirror has spherical aberration. Now, this can be completely rectified by using a parabolic shaped mirror. Mirror with parabolic shape of this kind, which is somewhat magnified. Note that the parabolic shape above has been exaggerated or magnified. So, this exaggerated parabolic mirror, what do you observe? All the light rays come to focus, there is only one focal point, right. All the light rays are getting reflected and getting focused at a particular point. Instead of many points that you have here, the marginal rays are getting focused at this point, whereas the paraxial rays are getting focused at this point, and this kind of defect that you have, which is called a spherical aberration, can be completely eliminated by replacing a concave mirror, a spherically shaped mirror, by a mirror which has got a parabolic shape. Parabolic shaped mirror will get all the light rays focused at a particular point. I have to tell you the reason why this kind of discrepancy or the defect occurs. In a moment I will come to that. How do you explain the reflected ray and all? So, you draw a tangent, you know, in the elementary education, the angle of incidence will be equal to the angle of reflection. The light rays are reflected, and the loss of reflection, it tells you that the angle of incidence should be equal to the angle of reflection. So, how will you find? You draw a tangent, okay, the tangent drawn will be like this, right. So, at this point the mirror is it got a curvature, so you draw a tangent and this is the angle of incidence. So, this is the angle of incidence, this is the angle of reflection. Okay. This light ray after being incident on this, it will be reflected. So, this will be the angle of incidence will be here, this is the angle of reflection. Whereas, for this light ray, the paraxial ray, the focusing is obtained here, because the tangent is to be drawn here. The way in which the tangents are drawn, the tangents will be having different inclinations, it should be obvious, right. The tangents will be having different inclinations, and that is the reason why they get focused at anyway the loss of reflection, the angle of incidence will be equal to the angle of reflection and the angle of incidence, both of them will be equal to one another. But the point is the tangents drawn will have different inclinations, that is the cause for the light rays to be getting focused at different points, leading to spherical aberration. Okay, that should be understood. So, a spherically shaped mirror will exhibit this kind of defect, namely spherical aberration. This is one of the defects which is caused by the spherically shaped mirrors. Similar to the case of mirrors, what about the lenses? You have the spherical aberration in lenses also. Let us have a monochromatic beam. You got a incoming parallel light rays passing through a lens, and again you got the marginal rays, the rays which are far away from the optic axis, and the paraxial rays. The point is, as I told you, the equation that you obtain in the case of mirror or a lens connecting the object distance, the image distance and the focal length, all the laws that you are getting, all the equations that you get, they will hold good if the angle that is made by the light rays on the lens or mirror are much smaller. So, the light rays which are very close to the optic axis will obey the equation that you get for by connecting the object distance, image distance, focal length. The equation that you get will hold good only for the light rays which are parallel to the optic axis and lying very close to the optic axis, only for these light rays. Okay. For these light rays, the relation that you have obtained, the mathematical relation that you have obtained will hold good. So, these light rays will come to a focus here. On the other hand, the marginal light rays that you got a light ray here, the marginal rays will be getting focused at this point. Therefore, what happens? The image is not will not be very sharp. You will be, the viewer will see a blurred image. You see the image here, it is a blurred image. So, for a given object, when the object is seen on the screen, when the object is passing through the lens and the image that you get will be blurred, the image that is captured by any optical instrument, or on the screen you have got object here, on the screen you can see the image at the elementary level. You have an object here, you get a real image or a virtual image. The images can be obtained on the screen. Okay. So, the image that you obtain will be blurred in this case, in the case of lenses. So, if the aperture of the lens is large, suppose the lens is very large, right, and very thick, then the image that you obtain, the image quality will be blurred, will be more defective. On the other hand, if you got a thin lens and with a small aperture, by having a small aperture, what do you do? You cut these rays, right, the marginal rays are cut off or stopped. Thereby you will be getting only one focal point. Instead of getting two focal points or many focal points, you will be getting the entire thing obtained at a particular point by using what are called stops, that is by cutting the marginal rays. You will be having only the paraxial rays. Okay. So, in spherical aberration, parallel light rays that pass through the central region of the lens focus farther away, right. The central region, they are getting focused at this point as you observe here, whereas the marginal light rays are getting focused at a nearer point, right. That is the light rays that pass through the edge of the lens, right, the edge of the lens, right. That is the one that leads to the problem. The result is many focal points, which leads to the formation of a blurred image. Now, I will show the blurred image that you have goes off if you use a proper lens. It is called a perfect lens. The quest for one and only one focal point. So, you are looking for only one focal point, then you will be getting a image which is crisp and clear. You have got a crisp and clear image of the object, and if there were a perfect lens, all light rays would be guided through one and only one focal point, and the resulting image would be a perfectly clear point. So, you got only one focal point by having what is called perfect lens. Now, I will tell you what we mean by perfect lens and other things later, and we now pass on to a very interesting things. Supposing you have, we are talking about the defects, right. What is the defect that you get due to what is called chromatic aberration? I have been talking about spherical aberration, then the other defects are chromatic aberration, distortion, so on. Now, this picture is a nice picture where you observe, what do you observe? You see, when you get the image through a binocular or you take a photograph, what you observe is you see this is the real image of the building. Now, what do you observe here? The real image undergoes some kind of deformation or change, or that there is a defect, and you see here it is the chromatic aberration, right. Chroma is a color. So, this kind of you see this end now looks to be some bluish in color, right. The whole thing, you see the image is not clear as the original image. This is the original building, but the image that you catch through the lens is appearing to be somewhat defective. The point to be noted is following: this edge is very different from this edge here, right, and this defect is due to chromatic aberration. The much more clear thing will be what is called distortion, the images that you get because of distortion. And I will show now, you have a wire gauze. Wire gauze, you have a number of wires, right. You have got a wire gauze like this, you have got a wire here, wire here, wire here, okay, number of wires, and you have got along this direction also you have got wires. So, you have got object here, you have got a wire gauze, and then you see the image. This image will be free from, if it is free from defect, then the image that is obtained will be shown as shown in figure 1. There is no distortion. On the other hand, if you are having a lens, you have got an object here, you have got a lens, and the image is, and the screen is here. Depending upon the nature of the lens, you will be getting some kind of distorted image, and this distortion is called barrel distortion, because it looks like a barrel, right. It is called a barrel distortion. When do you get barrel distortion? Supposing the object, this object, right, you now remember this object, the wire gauze is kept here, and lens is kept here, and you have got a screen. On the screen, the image that you obtain will be of this shape. It will be looking like a barrel. the rectangle becomes looks like a barrel. So, this is called a barrel distortion. On the other hand, sometimes depending upon the nature of the lens, you will be having pin cushion distortion. It becomes bent like this, right, and at the center you have the pin cushion, right, a pin cushion distortion like a cushion. So, pin cushion, somebody sits here, then pin cushion distortion. So, it gets bent. Similarly, this also region also gets bent. All these regions are getting bent. Here they are getting bent inward, right. Here they are getting bent outward. This becomes the barrel. This is what is called a pin cushion distortion. So, these distortions are produced by lenses. This is a real object. This is a real object. This real object, when the light rays coming from the real object are passing through different lenses, either you will be ending up with a barrel type distortion or a pin cushion distortion. This is the clearest way of explaining to a student what kinds of images you are obtaining when light rays are passing from an object and the images that you catch on the screen. So, when an object of this kind is kept at a point and the light rays coming from this object, when they are passing through a lens, will produce either a barrel type distortion or will lead to pin cushion distortion. With this we come to the end of lecture 1, and before that we will have the summary and the question sessions. So, the summary goes as follows: the departures of real images from the ideal images, the actual images in respect of the size, shape and position are called aberrations. Anything which is deviating from the actual image, the real image and the one that you obtain, the difference is called the defect or the aberration. An aberration is any failure of a mirror or a lens to behave precisely according to the simple formulae. The laws of nature or the formulae that you have cannot be obeyed by the light rays, right, all light rays. So, the formula that we obtain connecting the image distance, object distance and the focal length, they all hold good only under certain approximations, and these defects are due to the inevitable consequences of the laws of reflection or refraction at spherical surfaces. Let us now move on to the question session. The questions that I have in front of you are: what is meant by aberration? Name the defects of images. What is meant by spherical aberration? What do you understand by distortion? What are the causes that lead to the defects of images? With this we come to the end of the lecture 1. The remaining things regarding the various defects, which will be ought to be discussed in detail, we will see in the lectures to come. Thank you.